So far we've developed a divide and conquer approach to counting the number of inversions of an array. So we're going to split the array in two parts, recursively count inversions on the left, on the right. We've identified the key challenge as counting the number of split inversions quickly, where a split inversion means that the earlier index is on the left half of the array, the second index is on the right half of the array. These are precisely inversions that are going to be missed by both of our recursive calls. And the crux of the problem is that there might be as many as quadratic split inversions, yet somehow to get the runtime we want, we need to do it in linear time. So here's the really nice idea which is going to let us do that. The idea is to piggyback on merge sort. By which I mean we're actually going to demand a bit more of our recursive calls to make the job of counting the number of split recursions easier. This is analogous to when you're doing a proof by induction. Sometimes by making the inductive hypothesis stronger, that's what lets you push through the inductive proof. So we're going to ask our recursive calls to not only count inversions in the array that they're passed, but also along the way to sort the array. And hey, why not? We know sorting is fast. Merge sort will do it in n log n time, which is the runtime we're shooting for. So why not just throw that in? Maybe it'll help us in the combined step, and as we'll see, it will. So what is this bias? Why should we demand more of our recursive calls? Well, as we'll see in a couple slides, the merge subroutine almost seems designed just to count the number of split inversions. As we'll see, as you merge two sorted subarrays, you will naturally uncover all of the split inversions. So let me just be a little bit more clear about how our previous high-level algorithm is going to now be souped up so that the recursive calls sort as well. So here's the high-level algorithm we proposed before, where we just recursively count inversions on the left side, on the right side, and then we have some currently unimplemented subroutine count split inv, which is responsible for counting the number of split inversions. So we're just going to augment this as follows. So instead of being called count, now we're going to call it sort and count. So that's going to be the name of our algorithm. The recursive calls again just invoke sort and count. And so now we know each of those will not only count the number of inversions in the subarray, but also return a sorted version. So out from the first one, we're going to get array B back, which is the sorted version of the array that we passed it. And we'll get a sorted array C back from the second recursive call, the sorted version of the array that we passed it. And now the count split inversions, now in addition to counting split inversions, it's responsible for merging the two sorted subarrays B and C. So count split if will be responsible for outputting an array D, which is a sorted version of the original input array A. And so I should also rename our unimplemented subroutine to reflect its now more ambitious agenda. So we'll call this merge and count split inv. Now, we shouldn't be intimidated by asking our combining subroutine to merge the two sorted subarrays B and C, because we've already seen we know how to do that in linear time. So the question is just piggybacking on that work, can we also count the number of split inversions in an additional linear time? We'll see that we can, although that's certainly not obvious. So you should again at this point have the question, why on earth are we doing this? Why are we just making ourselves do more work? And again, the hope is that the payoff is somehow counting split inversions becomes easier by asking our recursive calls to do this additional work of sorting. So to develop some intuition for why that's true, why merging naturally uncovers the number of split inversions, let's recall what the definition of just the original merge subroutine for merge sort was. So here's the same pseudocode we went through several videos ago. I have renamed the letters of the arrays to be consistent with the current notation. So we're given two sorted subarrays. These come back from recursive calls. I'm calling them B and C. They both have length n over 2. And we're responsible for producing the sorted combination of B and C. So that's an output array D of length n. And again, the idea is simple. You just take the two sorted subarrays B and C, and then you take the output array D, which you're responsible for populating, and using index k, you're going to traverse the output array D from left to right. That's what this outer for loop here does. And you're going to maintain pointers I and j to the sorted subarrays B and C respectively. And the only observation is that whatever the minimum element that you haven't copied over to D yet is, it's got to be either the leftmost element of B that you haven't seen yet or the leftmost element of C that you haven't seen yet. B and C, by virtue of being sorted, the minimum element remaining has to be the next one available to either B or C. So you just proceed in the obvious way. You compare the two candidates for the next one to copy over. You look at B of I, you look at C of j. Whichever one is smaller, you copy over. So the first part of the if statement is for when B contains the smaller one. The second part of the else statement is for when C contains the smaller one. Okay, so that's how merge works. You go down B and C in parallel, populating D in sorted order from left to right. Now, to get some feel for what on earth any of this has to do with the split inversions of an array, I want you to think about an input array A that has the following property. That has the property that there are no split inversions whatsoever. So every inversion in this input array A is going to be either a left inversion, so both indices are at most n over 2, or a right inversion, so both indices are strictly greater than n over 2. Now the question is, given such an array A, once you're merging at this step, what do the sorted subarrays B and C look like for an input array A that has no split inversions? The correct answer is the second one, that if you have an array with no split inversions, then everything in the first half is less than everything in the second half. Why? Well, consider the contrapositive. Suppose you had even one element in the first half which was bigger than any element in the second half. That pair of elements alone would constitute a split inversion. Okay, so if you have no split inversions, then everything on the left is smaller than everything in the right half of the array. Now, more to the point, think about the execution of the merge subroutine on an array with this property, on an input array A, where everything in the left half is less than everything in the right half. What is merge going to do? Right, so remember, it's always looking for whichever is smaller, the first element of remaining in B or the first element remaining in C, and that's what it copies over. Well, if everything in B is less than everything in C, everything in B is going to get copied over into the output array D before C ever gets touched. Okay, so merge has an unusually trivial execution on input arrays with no split inversions, with zero split inversions. First, it just goes through B and copies it over. Then it just concatenates C. Okay, there's no interleaving between the two. So no split inversions means nothing gets copied from C until it absolutely has to, until B is exhausted. So this suggests that, perhaps, copying elements over from the second subarray C has something to do with the number of split inversions in the original array. And that is in fact the case. So we're going to see a general pattern about copies from the second element C, second array C, into the output array, exposing split inversions in the original input array A. So let's look at a more detailed example to see what that pattern is. So let's return to the example in the previous video, which is an array with 6 elements ordered 1, 3, 5, 2, 4, 6. So we do our recursive call, and in fact the left half of the array is sorted and the right half of the array is already sorted. So no sorting work is going to be done, and you're actually going to get 0 inversions for both our recursive calls. Remember, in this example it turns out all of the inversions are split inversions. So now let's trace through the merge subroutine invoked on these two sorted subarrays and try to spot a connection with the number of split inversions in the original 6-element array. So we initialize indices I and j to point to the first element of each of these subarrays. So this left one is B and this right one is C, and the output is D. Now the first thing we do is we copy the 1 over from B into the output array. So 1 goes there, and we advance this index over to the 3. And here nothing really interesting happens. There's no reason to count any split inversions, and indeed the number 1 is not involved in any split inversions because 1 is smaller than all of the other elements, and it's also in the first index. Things are much more interesting when we copy over the element 2 from the second array C. And notice at this point we have diverged from the trivial execution that we would see with an array with no split inversions. Now we're copying something over from C before we've exhausted copying B. So we're hoping this will expose some split inversions. So we copy over the 2 and we advance the second pointer j into C. And the thing to notice is this exposes 2 split inversions, the 2 split inversions that involve the element 2. And those inversions are 3, 2 and 5, 2. So why did this happen? Well, the reason we copied 2 over is because it's smaller than all the elements we haven't yet looked at in both B and C. So in particular, 2 is smaller than the remaining elements in B, the 3 and the 5, but also because B is the left array, the indices of the 3 and 5 have to be less than the index of this 2. So these are inversions. 2 is further to the right in the original input array, and yet it's smaller than these remaining elements in B. So there are 2 elements remaining in B, and those are the 2 split inversions that involve the element 2. So now let's go back to the merging subroutine. So what happens next? Well, next we make a copy from the first array, and we sort of realize that nothing really interesting happens when we copy from the first array, at least with respect to split inversions. Then we copy the 4 over, and yet again we discover a split inversion, the remaining one, which is 5, 4. Again, the reason is, given that 4 was copied over before what's left in B, it's got to be smaller than it, but by virtue of being in the rightmost array, it's also got to have a bigger index, so it's got to be a split inversion. And now the rest of the merge subroutine executes without any real incident. The 5 gets copied over, and we know copies from the left array are boring, and then we copy the 6 over, and copies from the right array are generally interesting, but not if the left array is empty. That doesn't involve any split inversions. And you will recall from the earlier video that these were the inversions in the original array, 3, 2, 5, 2, and 5, 4. We discovered them all in an automated method by just keeping an eye out when we copy from the right array C. So this is indeed a general principle, so let me state the general claim. So the claim is not just in this specific example, in this specific execution, but no matter what the input array is, no matter how many split inversions there might be, the split inversions that involve an element of the second half of the array are precisely those elements remaining in the first array when that element gets copied over to the output array. So this is exactly the pattern that we saw in the example. So on the right array, C, we had the elements 2, 4, and 6. Remember, every split inversion has to, by definition, involve one element from the first half and one element from the second half. So to count the split inversions, we can just group them according to which element of the second array that they involve. So out of the 2, 4, and 6, the 2 is involved in the split inversions 3, 2, and 5, 2. The 3 and the 5 were exactly the elements remaining in B when we copied over 2. The split inversions involving 4 is exactly the inversion 5, 4, and 5 is exactly the element that was remaining in B when we copied over the 4. There's no split inversions involving 6, and indeed the element B was empty when we copied the 6 over into the output array D. So what's the general argument? Well, it's quite simple. Let's just zoom in and fixate on a particular element X that belongs to that first half of the array, that's amongst the first half of the elements. And let's just examine which Y's, so which elements of the second array, the second half of the original input array, are involved in split inversions with X. So there are two cases, depending on whether X is copied over into the output array D before or after Y. Now, if X is copied to the output before Y, well then since the output's in sorted order, it means X has got to be less than Y, so there's not going to be any split inversion. On the other hand, if Y is copied to the output D before X, then again, because we populate D left to right in sorted order, that's got to mean that Y is less than X. Now, X is still hanging out in the left array, so it has a less index than Y. Y comes from the right array, so this is indeed a split inversion. So putting these two together, it says that the elements X of the array B that form split inversions with Y are precisely those that are going to get copied to the output array after Y. So those are exactly the number of elements remaining in B when Y gets copied over. So that proves the general claim. So this slide was really the key insight. Now that we understand exactly why counting split inversions is easy as we're merging together two sorted subarrays, it's a simple matter to just translate this into code and get a linear time implementation of a subroutine that both merges and counts the number of split inversions, which then in the overall recursive algorithm will have n log n running time just as in merge sort. So let's just spend a quick minute filling in those details. So I'm not going to write out the pseudocode, I'm just going to write out what you need to augment the merge pseudocode discussed a few slides ago by in order to count split inversions as you're doing the merging. And this will follow immediately from the previous claim, which indicated how split inversions relate to the number of elements remaining in the left array as you're doing the merge. So the idea is the natural one, as you're doing the merging, according to the previous pseudocode of the two sorted subarrays, you just keep a running total of the number of split inversions that you've encountered. Right, so you've got your sorted subarray B, you've got your sorted subarray C, you're merging these into an output array D, and as you traverse through D and K goes from 1 to N, you just start the count at 0 and you increment it by something each time you do a copy over from either B or C. So what's the increment? Well, what did we just see? We saw that copies involving B don't count. We're not going to look at split inversions when we copy over from B, only when we look at them from C, right? Every split inversion involves exactly one element from each of B and C, so we may as well count them via the elements in C. And how many split inversions are involved with a given element of C? Well, it's exactly how many elements of B remain when it gets copied over. So that tells us how to increment this running count. And it follows immediately from the claim on the previous slide that this implementation of this running total counts precisely the number of split inversions that the original input array A possesses. And recall that the left inversions are counted by the first recursive call, the right inversions are counted by the second recursive call. Every inversion is either left or right or split. It's exactly one of those three types. So with our three different subroutines, the two recursive ones and this one here, we successfully count up all of the inversions of the original input array. So that's the correctness of the algorithm. What's the running time? Well, recall in merge sort, we began by just analyzing the running time of merge, and then we discussed the running time of the entire merge sort algorithm. Let's do the same thing here briefly. So what's the running time of this subroutine for this merging and simultaneously counting the number of split inversions? Well, there's the work that we do in the merging, and we already know that that's linear. And then the only additional work here is incrementing this running count, and that's constant time for each element of D, right? Each time we do a copy over, we do a single addition to our running count. So constant time per element of D, or linear time overall. So I'm being a little sloppy here. It's sloppy in a very conventional way, but it is a little sloppy by writing O of n plus O of n equals O of n. Be careful when you make statements like that, right? So if you added O of n to itself n times, it would not be O of n. But if you add O of n to itself a constant number of times, it is still O of n. So you might, as an exercise, want to write out a formal version of what this means. Basically, there's some constant C1 so that the merge step takes at most C1 n steps. There's a constant C2 so that the rest of the work is at most C2 times n steps. So when we add them, we get its most quantity C1 plus C2 times n steps, which is still big O of n because C1 plus C2 is a constant. Okay, so linear work for merge, linear work for the running count, so that's linear work in the subroutine overall. And now by exactly the same argument we used in merge sort, because we have two recursive calls on half the size, and we do linear work outside of the recursive calls, the overall running time is O of n log n. So we've really just piggybacked on merge sort up to the constant factor a little bit to do the counting along the way, but the running time remains big O of n log n.